After a brief introduction to radio telescopes, let's now try and look at the sources of radio emission in the sky. We've already discussed about Jansky's discovery of radio emission from the center of our galaxy, the Milky Way, and Grote Reber's efforts in making an antenna literally in his backyard and trying to image the emission which Jansky had discovered. And as I mentioned earlier, that he initially tried to detect it at higher frequencies and made no detection at 3319 megahertz. And it is only when he moved towards lower frequencies that he detected radio emission. And this is one of the very early maps of our galaxy, the Milky Way. And this is plotted in a coordinate system where this is the way the Milky Way appears, the equatorial coordinate system. And we also mentioned that when you look at the spectrum of emission, which Carl Jansky discovered and Grote Reber mapped at a different frequency, that it did not resemble either a blackbody spectrum or due to thermal free emission. And we learned, due to contributions of a number of astrophysicists, particularly Russian astrophysicists, that the emission is due to synchrotron radiation. Synchrotron radiation, which is radiation due to ultra-relativistic particles moving in a magnetic field. These ultra-relativistic particles are electrons which are moving at almost the velocity of light, very close to it, and moving around in a magnetic field of our galaxy. One may ask, how are these high-energy electrons generated? They're usually generated in, for example, one of the sources would be supernova remnants, where high-energy particles are generated in these massive explosions that take place. So these particles keep moving around in the magnetic field and radiating and diffuse in the general magnetic field of the galaxy. So now this is a more recent map of our galaxy. This is plotted in a coordinate system where this is the plane of the galaxy. This is towards the center of the galaxy. And what is shown over here is a map, a reprocessed image of the sky at 408 megahertz. This particular image was made by Glenn Haslam and his collaborators using telescopes at both the northern and the southern hemisphere, because to make an entire image of the whole sky, you don't have to have telescopes in both the hemispheres. From the north, you would not be able to see deep down in the southern hemisphere. And similarly, from Australia, you're not going to see right towards the northern latitudes. Now, what you see over here is that emission is largely from the plane of our galaxy. And in this particular reconstruction, they've subtracted, I think, some sources as well. And what you find over here is there is a diffused loop of emission, which is called a North Polar Spur. And the intensity is maximum towards the center of our galaxy along the galactic plane. Right over here are the Magellanic Clouds, okay? And along the plane, you can also see Cassiopeia and Cygnus region. Now, at low frequencies, as we mentioned with Jansky's and Grote Reber's observations as well, that you will pick up largely non-thermal emission. Non-thermal emission because that is more prominent at low frequencies than at higher frequencies. At higher frequencies, you'll also start picking up emission due to ionized regions of hydrogen, because as we saw that they have a spectrum which is relatively flat compared to the non-thermal spectrum of synchrotron radiation. Again, I repeat that non-thermal because here it is neither a blackbody radiation nor due to particles which are in thermodynamic equilibrium and not from a Maxwell-Boltzmann distribution of particles which are radiating, but even the radiating particles have a polar distribution so that there are many more particles radiating at lower energies than at higher energies. On the right-hand side, you can see a similar all-sky map of our galaxy, but this has been made at a slightly higher frequency. 1420 megahertz formed from surveys in the northern sky as well as with the southern sky. And the resolutions are somewhat different, but not hugely. That the upper one is about 56 arc minutes. So these are relatively coarse resolutions, as you can see, at 35.4 arc minutes at 1400 megahertz. But if you were to look at it in more detail, then at the higher frequencies, you will find that the regions of non-thermal emission, regions of thermal emission, such as from regions of ionized hydrogen, H2 regions, would be a bit more prominent than at the lower frequencies, okay? And we can actually zoom in and look at what we'll do is zoom in and look at individual sources that could contribute to this emission, as well as a large-scale diffuse emission by looking at images of galaxies and images of radio sources in our galaxy to start off with. By now, you're all familiar with the Orion Nebula. Okay, this is on the left is the HST image, which we had discussed in detail earlier. And in the middle panel, what you have is a radio image of the Orion Nebula at radio frequencies made by combining data from the very large array, from the VLA, the Very Large Array, and the Green Bank telescope. Now, you may ask, why do you combine data from two telescopes? The reason is as follows, that as we mentioned, that depending on the resolution, you will pick up structures on different scales. For example, if you, in the extreme case, if you remember the image of the black hole made by the Event Horizon Telescope, then there was hardly any extended emission which was visible. Because when you observe a source with high angular resolution, then you tend to resolve out the more diffuse extended emission that you see. But by combining data from different telescopes, you can try and synthesize and put together the structures on different angular scales. The Green Bank telescope, being a single dish, would be sensitive to all the large-scale diffuse extended emission, whereas a VLA would be sensitive to the smaller scale structures. So combining data from different telescopes, you can put together the structures on different angular scales, all right? And get a more complete picture of both the small scale structure as well as the large scale structure. And on the right, what is shown over here is a radio spectrum of the Orion Nebula or similar H2 regions, okay? Now, on the right-hand part of the spectrum over here, the emission is what is referred to as optically thin. Optically thin means that the radiation is not getting absorbed. Radiation is coming through as it is being emitted. Whereas if the radiation is getting absorbed by dense plasma, either inside it or outside it, then the emission would actually start decreasing. And this is referred when the radiation gets absorbed, it is referred to as the optically thick region. This is the optically thick, this is the optically thin, and there is a sort of transition region over here where it goes from optically thin to optically thick. So you can see that at low frequencies, if it becomes optically thick, it will be more difficult to detect it because the flux density will go down. Okay, and here again, one has to make measurements at a number of frequencies to try and determine this curve reliably. But at the higher frequency part over here, you can see that it is relatively flat. It is nu to the power of minus 0.1, okay? And whereas here it is rapidly increasing with frequency. You can see it's nu squared over here. And so it's not going to decrease dramatically as you go higher in frequency. And that is why these regions are more easily picked up in the observations or surveys of the sky, if you do it at a higher frequency. For example, if you were to survey the plane of our galaxy at a high frequency, then you're more likely to pick up these regions of ionized hydrogen than if you did it at very low frequencies or low frequencies. I will highlight to you just some of the objects which are there, or which you will detect in our galaxy, and also will be there in other galaxies, but obviously because being closer and one can observe them in far greater detail than if you saw them in other galaxies. This is an image, these are images of planetary nebulae. What are planetary nebulae? That is something we'll look at it in more detail when we look at stars and their evolution. But basically, during the late stages of evolution of stars like our sun, which are low mass stars, they shed the outer envelopes before becoming and settling down as a white dwarf star. Okay, and in these stages, in this stage, these are optical images made by the Hubble Space Telescope of a variety of planetary nebulae. You can see it has a range of structures. The way it evolves will depend on the star and its environment as well. And this is a radio image of a planetary nebula called K3-35. But this is to show you another example of emission, of radio emission from galactic objects. And this also has a lot of interesting shapes which one can sort of study at radio wavelengths. And this is largely, again, thermal emission. These are particles which are being accelerated in the ionized plasma by the Coulombic potentials. Okay. Here's another class of objects in our galaxy, which radio observations pick up reasonably easily. And these are the supernova remnants. Now, we talked about the evolution of a low mass star like our sun, but if there are stars which are much more massive, say 5 times the mass of our sun or even larger, then they would end their lives in a massive explosion called a supernova, and giving rise to a supernova remnant, which will travel out into interstellar space and forming interesting shapes given the density of the external medium as well. But often they would be sort of a shell kind of structure which you pick up at radio frequencies. In this particular image, what you can see is these are false colors over here. This is the red. In red is shown the radio emission. In optical is shown in green over here, and X-rays, which are hot gas, is shown in blue over here. And the radio emission is usually non-thermal over here, as the ejector moves through the interstellar medium of the galaxy. It compresses the general interstellar medium, giving rise to stronger magnetic fields, and also the particles which are being accelerated by the shocks in this explosion, releasing about 10 to the power of 53 ergs or so, that they would give rise to synchrotron emission, which we mentioned earlier, by moving around or gyrating in the magnetic field of this remnant. Now, as I mentioned, a lot of supernova remnants have a shell kind of structure, which you see in this particular supernova remnant. But there are also cases which are called filled remnants or playarions, where all particles are also accelerated in the interior, giving rise to a fill kind of structures. You can get hot X-rays from here, as well as optical emission, which is shown in this particular picture. But right now we are focusing on the radio aspect of it. And radio, because these massive stars are largely in the disk of the galaxy, where star formation is taking place in the molecular clouds, which are effectively the stellar nurseries, that radio observations have been very useful in trying to catalog supernova remnants. Because as we learned that the optical light, because of the small wavelength, are more prone to absorption and extinction, whereas at radio region, you can probe right into the nuclear region of the galaxy, along the plane of the galaxy. And so to try and identify supernova remnants, the radio surveys have been extremely helpful. When the star explodes, when this massive star explodes, what does it leave behind? Low mass stars, as we mentioned, leave behind a compact object called a white dwarf star, We'll look at the properties of these stellar remnants in a bit more detail when we study stars. But what about a massive star? The massive star leaves behind what is called a neutron star. Okay, a neutron star is effectively largely made of neutrons. It's extremely dense, and it has a mass of the order of a solar mass or more, a bit more, and it's only about 10 kilometers or so in diameter, in size. So you can see that it's an extremely compact object. Okay, and the star would have had some initial rotation. So conservation of angular momentum would lead to a neutron star, which is spinning very rapidly. And the field lines also attached to the neutron star has a dipolar form, and the fields are extremely strong, typically of the order of 10 to the power of 12 Gauss or so, although stronger magnetic fields are also known. Particles are accelerated along the polar axis over here, giving rise to pulse of radio emission, giving rise to emission along this axis. And if the spin axis of the neutron star and this magnetic axis are not aligned, then as it keeps rotating, and if this axis hits you, you'll see a pulse of emission. When we were discussing the history of astronomy and some of the important discoveries, I'd mentioned to you that this class of objects called pulsars was something which was discovered by Jocelyn Bell Burnell when she was a graduate student at Cambridge working with Anthony Hewish. On the left is a very slowed down version of Crab pulsars at 800 nanometers in the infrared region of the spectrum. The Crab pulsar has a pulse period of 33 milliseconds. And today we know that that pulsars can be rotating at very high, very short periods, short as about milliseconds or so. The fastest period, I think, is about 1.3 milliseconds. Okay, and what Jocelyn Bell Burnell had discovered was PSR 1919 plus 21. This is the name of the pulsar, and it had a period of about 1.337 seconds. Okay, and this has been timing of these periods of these pulsars have been one of the holy grails for detecting gravitational waves as well. So these pulsar periods, occasionally they may have a little bit of a quake, and there may be what is called a glitch, and the period will change. But when that does not happen, the pulsar periods are extremely steady, and they also slow down at a very, very slow rate, and that can all be measured by radio astronomers by making detailed observations of pulsars over a period of time. There have been a number of groups trying to time these pulsars very accurately. There's an international pulsar timing array. There's also an Indian pulsar timing array, which makes extensive observations with both a giant meter wave radio telescope and the UT radio telescope, which I mentioned earlier. And there are other groups as well, and they all combine and share the data. So when a gravitational wave strikes a particular part of the sky, then they would have an effect on the periods of pulsars. So by looking at accurate timing of pulsars, one hopes that one would be able to detect gravitational waves. As you know, gravitational waves have been directly detected, and the gravitational waves were first initially sort of inferred from observations of slowing down of pulsar in a binary system. Now these are more distant objects coming closer to us. This is a radio image of the sun. Okay, and you can see on the top left-hand corner that these are the frequencies as which the observations are being shown over here, and the website from where I've taken it is shown below. And the solar not only has the photosphere from which we see it at optical wavelengths, but it also has the chromosphere and the corona, and different physical processes play a role in trying to detect the emission in these different locations. On the right, over here, what I've shown is the frequencies at which emission can take place, and also the height above the surface from which this emission is detected. So you can see that closer to the surface of the sun, where magnetic fields play a role, you can also get gyro resonance or gyrosynchrotron emission. These are electrons moving in the magnetic field near the surface of the sun. As you go to higher heights, okay, and at lower frequencies as well, you will see emission due to bremsstrahlung and also various plasma processes which take place. So you can see on the image on the left that as you keep going to higher frequencies from lower frequencies, you tend to see more of the disk of the sun, whereas at low frequencies just now, you can see that the sun is much bigger, where you're detecting radio emission from the corona. And as you go to higher frequencies, you see more of the disk emission, the active regions over there, which are related to the sunspots, and all kinds of bursts which take place in the sun as well, different types of bursts of emission, the coronal mass ejections from the sun, in addition to the general solar wind. And radio astronomers spend a lot of time studying these bursts in detail and understanding what they might be telling us about the different plasma processes which are taking place on the surface of the sun. You can also see over here that when you look at the sun, the outer part is more visible at the lower frequencies. And as you go to higher frequencies, you're able to see far closer into the surface of the sun. Besides the sun, of course, we can see our own planetary systems, objects in our planetary system, both thermal and non-thermal emission. Jupiter, for example, has pretty strong magnetic fields, and there are also bursts which take place from Jupiter. And on the left is an image of the moon thermal emission, which was from Chris Salter with observations with the IREM telescope at 230 gigahertz. And on the right, I've shown a picture which was made by Imke de Putter in the recent conjunction of Jupiter and Saturn. We could look in the sky, and even with the naked eye or with a pair of binoculars, you could easily see the conjunction of Jupiter and Saturn. But here is a radio image at 15 gigahertz showing the images of Jupiter and Saturn, what it looked like during the conjunction at radio frequencies. This particular image is at a frequency of 15 gigahertz, which corresponds to a wavelength of 2 centimeters. Now, just to talk about the diffuse radio emission from our galaxy. Sitting inside, it is more difficult to visualize what it might look like. So I thought I would just sort of show you 2 images of spiral galaxies, which are similar to that of our own galaxy, and see what the emission looks like. Here is an image of M51, Messier 51, which is a face-on spiral galaxy. And you can see non-thermal radio emission along the disk of the galaxy, some of it roughly along the spiral arms of the galaxy. And there also seems to be an ordered component of the magnetic field. These little dots, little lines which you see, they indicate the direction of the magnetic field in this galaxy. This has been made with the Effelsberg telescope and by Rainer Beck and collaborators over there. Now, when you look at a galaxy, we obviously cannot turn it in different directions. That is the way it is located, oriented relative to us. But what you can see on the right is another galaxy, which is nearly edge-on. So if this galaxy was put edge-on, this is what it would look like. This is the disk of the galaxy. And here you can see that the diffusion of cosmic ray particles or electrons, relativistic particles, along the z-axis or perpendicular to the plane of the disk as well. That would be very difficult to make out in the case of a galaxy, which is face-on or nearly face-on. So high energy particles are being generated in galaxies where active star formation is also taking place. And these particles, diffuse in the interstellar medium of the galaxy. They travel along the disk of the galaxy as well as orthogonal to it. And these particles gyrating in the magnetic field of the galaxy gives rise to the synchrotron emission, which we talked about earlier, which was noted initially by Karl Jansky from the center of our galaxy and imaged and shown to have a non-thermal spectrum by Groth-Reber with an antenna which he built in his backyard. Today, of course, we have images which are far, far more sensitive in a variety of resolutions, bringing out both the large and the small scale structure. Just as in the case of in the optical region of the spectrum, radio astronomy has also contributed immensely to our understanding of the extragalactic universe. Okay, in terms of trying to find optical counterparts of radio sources. For example, the image of the sky, the radio sky, which I showed you while discussing about radio telescopes and sensitivity, that you saw lots of blobs of radio emission in the sky. Now, one naturally asks oneself, what are these objects? What is emitting this radio emission? Are they associated with galaxies? Or is it something different? And so the natural thing to do was to try and find counterparts of these radio sources. Are they positionally coincident with any other kind of object? Or are they just lying in empty space? So at that time, the most obvious thing to do was to correlate with the optical images, because there were images of the optical sky surveys were available. And I must stress over here that while trying to look at coincidences, you would also need good angular resolution. For example, if this particular source, Hercules A, which is image I've shown over here, if this particular image had a resolution which was as large as the picture I'm showing you, there's so many other galaxies which are over there. It would appear as one single point source. You'd never be able to be certain which galaxy it is associated with, or if it is associated with any galaxy at all. So just as in the discovery of quasars, which we mentioned in the history of astronomy or important developments in astronomy presentation or discussion, you need high angular resolution to be certain that a particular radio source is associated with a particular galaxy. And that was easier for some of the nearby galaxies. And those were the ones which were initially identified in the early days, because the images of the radio sources were rather coarse because the resolution was poor relative to what it is today. But the optical images of the nearby galaxies were also larger because they are closer. So the chances of just a chance coincidence was less if you had nearby galaxies. But on the other hand, in a given blob, there would be many more distant galaxies which would be part of it. So the initial galaxies which were identified were relatively nearby galaxies: Virgo A, Centaurus A, Hercules A, Fornax A, and slightly more distant Cygnus A. And you can see over here in Hercules A that there's all these blobs of emission seem to originate from the nucleus of a galaxy. They seem to be blowing bubbles or jets of plasma coming out from the nucleus of an active galaxy. And all these regions of emission which you see over here are due to, again, synchrotron emission. That is relativistic particles moving in the magnetic field in these lobes of emission. And the source of this emission is right in the nucleus. And these energies these lobes could have, total energy content could be of the order of 10 to the power of 60 ergs or so. So a huge amount of energy being generated in the nucleus of the galaxy and transported outwards over distances which could be millions and millions of light years across. So this was one of the very exotic class of objects in the extragalactic sky, which radio astronomy helped reveal. Okay. Now, on the large scales, I would just show you again the cosmic microwave background radiation. This is at millimeter wavelengths. I would ask you to sort of just find out the frequency at which it at which the spectrum peaks. This was given as one of the exercises, and this is almost a perfect black hole. So this is what lent a strong evidence in terms of a Big Bang model of the universe, a very fiery, hot origin of the universe when the radiation sort of decoupled and has constantly cooled since then. And the current temperature is about 2.73 or 2.725 degrees Kelvin. And you can see over there that it is almost, it's not almost, it's as good a black body as you can get. There are very tiny fluctuations, which was measured later by the Wilkinson microwave anisotropy probe WMAP, and more recently by the Planck mission. And these variations are the signatures of the structures which we form today, which formed the galaxies, one of which we all reside in. So this is just to give you a glimpse of the continuum emission at radio frequencies and some of the exciting discoveries that radio astronomers have made while looking at continuum wavelengths. Continuum means the emission is spread over a large range of wavelengths and does not correspond to a spectral line, which is due to transitions from quantized energy levels and occur at very particular or specific frequencies. Let us now look at a brief look at spectral lines in radio astronomy. This has also played a very important role. One of the most important lines in radio astronomy is the 21 centimeter line of neutral atomic hydrogen. You're familiar with the Lyman series, the Balmer series, etc., of hydrogen when the electrons are excited to different energy levels. But suppose the electron is completely in the ground state, and a lot of hydrogen is in the ground state. Then the only way of actually trying to detect this neutral atomic hydrogen, which is a very important component, is through this transition, which was predicted by Van der Hulst in 1944. And it was, I think, Jan Oort who suggested that one should look for a line at radio frequencies. And hydrogen being the most abundant element, it was not surprising that that this has played a very important role in our understanding of the universe. And after it was predicted, soon after the Second World War, there were different groups which detected this line in the US, in the Australia, and in the Netherlands as well. Okay. So what is this transition? When hydrogen is in the ground state, there is the spin of the proton. This is the quantum mechanical concept of the proton and the electron. And the spins could be aligned or it could be misaligned. Misaligned in the sense they're parallel or they could be antiparallel. And when the transition takes place, it gives out radiation at a very low frequency of 1420.405 752 megahertz. And as I said, this is one of the very important lines of astronomy. So the temperature, which is referred to as the spin or the excitation temperature, accounts for the distribution of the atoms between the two states, and the population between the two states is largely determined by the collisions between the atoms. If you look at the energy level in terms of electron volts, you can see that it is an extremely small value. And that is why the transition occurs at the radio part of the electromagnetic spectrum. Whereas you know that the Lyman alpha starts off in the ultraviolet and the Balmer series H alpha is in the optical region of the spectrum. They are at much higher energies and occur at much higher frequencies. Whereas this transition, which is referred to as the spin flip transition, occurs in the radio region of the spectrum. And because it is most so abundant that, and it is a particular line, by looking at the shifts of the line, you can make studies of the dynamics of galaxies as well. Here is a map, a sky map of neutral atomic hydrogen. in our galaxy. We looked at continuum maps earlier, but this is the H1 map, which you can see is largely confined over here to the disk of the galaxy. You can also see the large and the small Magellanic Cloud. And this again has been put together by observations of telescopes, both in the northern hemisphere and in the southern hemisphere. Okay, the Effelsberg telescope in Germany, a 100-meter telescope, and the 64-meter dish at Parkes have been put together to construct this all-sky map. When we look at our galaxy, we'll briefly look at how the rotation of our galaxy has been determined from studies of spectral lines, which is basically the 21-centimeter line of neutral atomic hydrogen. Okay. While on the theme of neutral atomic hydrogen, trying to find the dynamics of galaxies, I should also mention that while making an image of neutral atomic hydrogen in a galaxy, the atomic hydrogen can extend far beyond what you see at optical or visual wavelengths. These are regions where stars have not started forming, but where gas exists, neutral hydrogen gas exists. And this is a particular galaxy where NGC 2915, which I have taken out from a presentation by Raffaele Morganti, where you can see that neutral hydrogen is much more extended than the stars. Okay? The stars is right, this optical galaxy over here. All the various dots which you see are background objects, optical objects, but the blue is what shows you the neutral atomic hydrogen. And for example, now this gives you the intensity or how much hydrogen is there, but you can also map it in terms of velocity. For example, if this galaxy were rotating, then the gas which is coming towards you would be shifted towards the blue part of the spectrum, and the gas which is going away from you would be redshifted and appear at longer wavelengths. So you can go and study how this galaxy is rotating. And that has actually yielded very important results in understanding the dynamics of galaxies. And as we shall see, it has also been one of the very strong evidences for studying dark matter in galaxies. Now, we mentioned about dark matter in the context of Zwicky inferring the existence of dark matter while studying the Como cluster of galaxies, because the velocities of the galaxies required much more matter to be present in the cluster of galaxies. Then you could understand in terms of counting the number of galaxies and estimating the mass of each galaxy and adding that up. And that led to his suggestion of the existence of dark matter. Let's for a moment see how this works out in an individual galaxy. Now on the left, I plotted the velocity, the orbital speed in kilometers per second of the planets in our planetary system. Pluto is still plotted here. It is moving around the sun, although it is a minor planet now. But you can see over here that as you go away from the sun, this is the mean distance of the sun, with Mercury being the closest, then Venus, Earth, and it goes on. This is in terms of the astronomical units, which is a mean distance between the sun and the Earth. Now you can see over here that this motion can be understood in terms of Kepler's laws of motion, okay? Where if you equate the centrifugal force to the gravitational attraction, you will get a variation which is 1 upon root of r. Now, if you look at the way the hydrogen gas is moving, or even the stellar motions that one may determine, that that is not the case. Now, you might argue that, well, the sun is one compact object which has all the mass, and whereas in a galaxy, that is not the case. You have a bulge, but you have the disk where matter still exists, stars exist, okay? And so why should you expect a Keplerian fall? That is a very valid point, but you can actually model the distribution of stars and calculate from the mass to light ratios, you can calculate the distribution of mass, and you can go and estimate what you would expect the gas velocity, how it would decrease. So if you account for that in this particular galaxy, NGC 3198, you would find that this is what you would expect by taking account of the material in the disk as well as the bulge of the galaxy. You can see that in the early part, it almost follows like a solid body, V equal to R omega, where for a constant omega, you can see the velocity will keep increasing, just like a disk, for example. But then instead of decreasing, as you would expect, due to the gravitational influence of the content of the galaxy, which you can see, it does not decrease that way. It remains largely flat. There may be a minor wiggle here or there. This is true of our galaxy, as well as almost all external galaxies which have been studied. So the only way to understand this, or the only viable and way in a consistent, self-consistent way that one can understand this, is to try and invoke the existence of dark matter. Okay, and once you invoke the dark matter, you can try and explain the velocity of its flattening. So the dark matter which envelops the galaxy, and if you take account of both the dark matter and the disk material which you can see, then you can explain the flat rotation curve. So you can see that radio astronomy has also played an important role in terms of spectral lines and trying to understand the dynamics of galaxies. But that is not the only line which is important in radio astronomy. For example, in regions of ionized hydrogen, we talked about the H alpha line which is a recombination line to the n equal to 2 level in ionized regions. But there could be a lot of diffuse ionized gas in the interstellar medium of the galaxy. And as you know, that the radio frequency is low energy, right? Long wavelengths, which means the frequencies are low. So these are low energy phenomena. So you need transitions which will give rise to emission at low frequencies. And when can that happen? That can happen when the quantized energy levels where the transitions take place to are large. Because as you know from the structure of the atom, that when you go to higher energy, higher quantum numbers, for example, 109 alpha is what is given over here, which would be the transitions from n equal to 110 to n equal to 109, then the energy gap is small compared to the Lyman or the Balmer series. And this transition occurs at about 5 gigahertz or so. This shows you different recombination lines in the region of about 5 gigahertz. As an assignment, I've given you to explore lines at even lower frequencies. Do they occur, and what are the kind of quantum numbers that you would require? So radio recombination lines have been an important component in trying to understand diffuse ionized gas, diffuse gas in our galaxy, in addition to the neutral atomic hydrogen that I talked about, where we study the cold and the warm components of the interstellar medium, the material between stars in our galaxy. Besides recombination lines, the other very important line in radio astronomy comes from molecules. Okay, molecules can have different kinds of transitions. They can have electronic transitions, they can have vibrational modes, and they can have rotational modes. And these are all quantized as far as you will learn or have learned from your quantum mechanics. Now the quantized energy rotational levels occur in the millimeter region of the spectrum, many of these lines. And from a study of these lines, one can go and identify what are the kind of molecules that exist in the molecular clouds. We came across molecular clouds by talking about the Orion Nebula and star-forming regions. And you can see over here the the number of molecules that have been identified from this spectrum. People do very detailed calculations of different species which may exist and the frequencies at which the emission may be detected, and then go and try and observe with a radio telescope and see if they detect these lines. But the spectra are so rich that often a lot of these features are even unidentified. They are molecules which probably we have not thought about, but nature has managed to create in these dense molecular clouds. So these are another important component of the radio universe. I've not been absolutely exhaustive, but I've just tried to give you a flavor, because in addition to these, we will also get major emissions which take place at radio frequencies, and these have also played a very important role. While on the theme of molecular emissions, let me just go back again to the Orion constellation and the Orion molecular cloud. Okay, now this just gives you the stars of the Orion constellation. You can see Betelgeuse and Rigel. And once you start looking at the night sky when the monsoons are over, they'll become your friends if you keep looking at the Orion Nebula. It also points out the direction, the location of the Horsehead Nebulae, the stunning images which one sees from the HST as well. And the Orion Nebula is also marked over there. But what is marked in color is the molecular cloud. And this is a relatively lower resolution image, a high resolution image. There are even sort of lower resolution images which are available where you see a lot of this filled up and extending to even slightly greater lengths than what you see in this particular image. Now, this is a map of the molecular cloud. How do we image it? And what are the properties of a molecular cloud? So I've just given you a very rough guide over here that these are cold. The temperatures are less than about 100 K. They would also have a structure. They could have a warmer core, which is denser, but the typical temperatures are less than 100 K, and they're extremely dense compared to other components of the interstellar medium. This is about 10 to the power of 9 molecules per meter cubed, which is orders of magnitude denser than the general interstellar medium, which we will discuss about later. But this is still orders and orders of magnitude less dense than the atmosphere. For example, the room which you're sitting in and which I'm sitting in could have about 10 to the power of 25 molecules per meter cube. So you can see that this is about 16 orders of magnitude less dense, but yet these are the densest and coldest regions in the interstellar medium. And to form stars, you need clouds to collapse and fragment and form stars with a range of masses. And these are the stellar nurseries where new stars are born. And when these massive stars which are born ionize the gas, you get these regions of ionized hydrogen. So carbon monoxide is a good tracer because that is a transition which you can detect easily at radio frequencies, although hydrogen is far more abundant. In these cold regions, you would get molecular hydrogen. And as I mentioned, in molecules, you'll get transitions which are electronic, vibration, and rotational. Vibrational lines you might detect in the infrared, electronic in the optical, and the rotation energy levels in the radio region of the spectrum. I'll give you a very brief description of the energy levels that one may see at radio frequencies from carbon monoxide without actually, even if you have not done quantum mechanics, just to know that the energy levels are quantized would be adequate for this purpose. Okay, and the angular momentum is given by J squared equal to J into J plus 1 H cross squared. H cross is H upon 2 pi, and J can take the values 0, 1, 2, etc. And as in classical mechanics, the energy is given by J squared upon 2I, right? I is the moment of inertia, okay? And I is nothing but mu into R squared, where mu is a reduced mass of the molecule. So mu would be equal to 1 upon mu would be 1 upon m1 plus 1 upon m2. so that you can get mu is equal to m1 m2 plus divided by m1 plus m2. That is the reduced mass, and R is the equilibrium spacing of the nuclei of carbon monoxide. Now let's consider transitions which are quantized so that you have to have delta G is equal to plus or minus 1. And suppose it makes a transition from J to J minus 1, okay, emitting a photon of energy h nu. So energy Ej minus energy at J minus 1, okay, and because this is given by J squared upon 2I, you can express it as J into J plus 1 minus J minus 1 into J multiplied by h cross squared upon 2I. A simple algebra will show you that that is equal to J h cross squared upon I, and you can further simplify it to get the frequency at which you're going to see this emission. That is given by JH upon 4 pi squared I, okay? And I is nothing but the moment of inertia, okay? Now CO, the molecular weight, the mean molecular mass, reduced mass, is 6.859 atomic mass units, and this is in kilograms over here. This is the rotational, this is the average distance between the two nuclei. Okay. Now you can see that you can calculate from here, okay, that J equal to 1 to 0. If you plug in these numbers, you will get a frequency of 115 gigahertz, which is 2.6 millimeters. 2 to 1, you will get a frequency of 230 gigahertz, which is 1.3 millimeters. As you go factor of 2 higher, 3 to 2 will give you 345 gigahertz, 0.87 millimeters. So this is often referred to because of the spacing as a rotational ladder of the CO molecule. So at 115 gigahertz, you tune your equipment to measure, to take measurements, and you can go and trace out the carbon monoxide emission from this molecular cloud and other molecular clouds as well. And depending on the resolution again, you will see structures in different scales. If your interferometer has higher angular resolution, you will pick up the more compact spots, just as you saw for our own galaxy. Whereas if you had, coarser resolution, you'll pick out a large scale structure, but a large scale structure would be seen more extended than if you had higher resolution, where you would pick up the more compact regions of emission. With this introduction to both continuum and line emission at radio frequencies, I would like to sort of first discuss what is, that suppose you had a blob of emission, how would you distinguish whether it is from a supernova remnant or a region of ionized hydrogen? What I've shown in this image is a picture taken with the Meerkat radio telescope. That is something which I mentioned to you while talking about the square kilometer array being built in South Africa. And Meerkat is also a small animal which is commonly seen in South Africa. But KAT actually earlier stood for the Karoo Array Telescope, and extensions of that has been named Meerkat. And what has been marked over here is a very stunning image, actually. You can see various filaments, non-thermal filaments these are, and we still got to understand how they form. Right in the center over here is Sagittarius A star, which harbors a black hole of a few million solar masses. A supernova remnant is marked over here, SNR 0.9 plus 0.1, which is given by this name is from the galactic coordinates of the object. And there is a region marked over here called Sagittarius C, which hosts an H2 region, a well-known H2 region, which is about 10 parsecs in size and ionized by several hot massive stars. Now, suppose I had just two blobs of emission in the sky. from radio frequencies, how would I make out that one is a region, is a supernova remnant, and the other is a region of ionized hydrogen? This is what I'd like to discuss briefly. Any one of you would like to say something? Let me just mention that a supernova remnant has a non-thermal spectrum, right? Non-thermal means if you plot log S versus log nu, then it'll have a power law with a slope, which could be about 0.4, 0.5 or steeper, but it will not have a thermal spectrum similar to that of a region of ionized hydrogen. We saw the spectrum of the Orion Nebula, that H2 regions would be similar. Other H2 regions would also have a similar spectrum. The flux density may change, but in the optically thin region of the spectrum, it will have a slope which is very gentle of about 0.1. And in the optically thick part, it will actually turn over at lower frequencies. The optically thin part, it will have 0.1. So from the spectrum, you will get an idea. Also, if you had higher resolution observations, supernova remnants would often show a shell kind of structure. That is where the magnetic field has been compressed. As the explosion of a star, the remnants of it move outwards into the interstellar medium, and particles are accelerated in this region. But not all supernova remnants have a shell kind of structure. You can also have a filled supernova remnant called plerions, where particles are accelerated by central object within the remnant as well. So structure will give you another hint of whether it's a supernova remnant or an H2 region, in addition to the spectrum. But the other aspect which we have not discussed in detail over here is the polarization of the radio emission. Because there would be a uniform component as well as the field lines are getting compressed and particles are being accelerated, that the non-thermal synchrotron emission would be polarized, right? Whereas in a H2 region where particles are moving about randomly in the Coulombic potential, the emission is going to be unpolarized. So the spectral index, structure, and polarization would all give you clues towards understanding whether a region of radio emission in the sky is due to a supernova remnant or a region of ionized hydrogen. These are just a few questions I've given for you to mull over at a later period of time. One is a radio galaxy to redshift of 0.202, which is at a luminosity distance of 1000 megaparsec. 1 parsec, which we will define later as we go along, is 3.0856 into 10 to the power of 16 meters. Its flux density at 400 megahertz is 10 Janskys. I want you to just calculate the luminosity using the inverse square law, right? Which you're all familiar with. Don't worry about corrections due to motion of the galaxy, but just apply the straightforward inverse square law and calculate what its luminosity would be. Then while discussing recombination lines, I mentioned about radio recombination lines at even higher values of the principal quantum number. So I want you to estimate the frequency at which the H272 alpha line would be emitted and which telescopes in India are capable of observing this line. Okay. Once you determine the frequency, then you got to estimate, find out which telescopes in India are capable of observing this line. The third assignment I've asked you to ponder over is the spontaneous transition probability for the 21 centimeter line of atomic hydrogen is 2.85 into 10 to the power of minus 15 per second. So estimate the time scale for a single transition. Okay, so that would be the inverse of it, and discuss whether this makes it easy to detect the line, say, from our galaxy.